Okay, so now we are going to solve a problem which has been very frequently asked in interviews. Okay, so we will be given a binary tree. Okay, before we move ahead, let me ask you a very quick MCQ kind of question. So we have a binary tree, okay? We have a binary tree with n nodes. What can be the maximum value of its height? Yeah, maximum value of the height will be n. And when will that happen? That will happen if all the n nodes are lying along the same line, which is the case of a skewed tree. Okay, my next question is, what will be the minimum value of height of a binary tree? If there are n nodes, okay? Let's take example only. Let's say n is equals to 7. If n is equals to 7, you have got 1, 2, 3, 4, 5, 6, 7. 7 nodes along the same line. Here the height is 7. And if there are 7 nodes, what will be the minimum height? Minimum height will happen when you have got a perfect tree. This case, here the height is 3. Does it make sense? Yes or no? Correct? Yeah. And I had told you that when you have got a perfect tree like that, comprising of n nodes, then the height of this is log of n base 2. Correct? So I can say that if there are n nodes, then the minimum value of height will be log n base 2, and the maximum value of height will be order n. And it all depends upon what is the structure of the tree. If it is skewed, it will be a tree having huge height. And if it is perfectly balanced, then it will be log of n base 2. Let's look at that question now. We have been given a binary tree, and what we want to do is we want to print all the root to leaf paths. Print all the root to leaf paths. So let's say your binary tree is like that. How many root to leaf paths are there in this tree? There are 3 root to leaf paths. Can I say that number of root to leaf paths will simply be equal to number of leaves? Isn't it? Like, see, there is only one root, but there are multiple leaves. So this is one path. So this is 3, 4, 5. And this is another path. This is 3, 4, 7. And that is the final path, which is 3, 2, 9. So similarly, there can be multiple root to leaf paths. I want you to write a code which prints this data, which you can see right now on the board. This is a problem which you can easily solve using recursion again. So let's look at the board now, everyone. This is quite important. Let's say there is a big tree, okay? There is a very big tree. I'm just drawing a small portion of it. So let's say it has an edge coming from some node, and here you have got a 4, and here you have got a left subtree of 4, and here you have got a right subtree of 4. It's a big tree, by the way, okay? And there is root somewhere. Let's say root is present over here, something like that. Now, answer me one thing. There will be some root to leaf paths which are present in this left subtree. When I say present in left subtree, I mean to say that there will be some root to leaf paths whose leaves are present in this left subtree. And there will be some root to leaf paths whose leaves are present in this right subtree. Can I say all such paths that cross this 4 and land here, 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 or here will have 4 in them? Just think, any path that goes like that, that, or that will definitely have 4 in them. So it means that if I am there at a node, let's say I am doing a recursion on this tree. I'm visiting the nodes one after the other, okay? And I'm doing that using recursion. So if let's say I am at 4, then it means that all the paths that cross 4 will have 4 in them. So how many paths are there which cross 4? This is one path, this is another path, and both the paths have 4 in them. So what I'll do is whenever I am at a node, I'll put that node in an array. or in a list or in a vector, whatsoever you want. Okay. And after putting that in a particular list or vector, I'll make a call to the left subtree and I'll make a call to the right subtree. And while making those calls, I'll pass that vector or I'll pass that list. Okay. This is the idea that I'm trying to convey. So let's just take a quick example. I'll draw. So look at this particular tree. What I'm going to do is I'm going to make a call at this particular node. When I make a call at this particular node, let me draw it. Let's say this node is 3. And I'll pass over here an empty list, an empty array, whatsoever you say. Okay. And now, because I am at this node 3, I know for sure that all the paths that passes through 3 will be having 3 in them. So the first thing I'll do is I'll push this 3 in this vector or array, whatsoever you say, and then I'll make a call to the left child and the right child. So when you push this 3 inside this, you will have 3 over here, and then you will make a call to the left child, which is 4. Okay, and then you will also make a call to the right child. So 3 has been pushed and the right child is this 2. Now I'll keep doing this thing in a repeat mode. So when I am at this node 4, I know that all the paths that cross this 4 will have 4 in them. So I'll push this 4 in that vector, and that way I'll have 3, 4 with me, and I'll make a call to the left and right child of 4. So you make a call to the left child, you make a call to 5, and now you have 3, 4 with you. Similarly, you make a call to the right child, you go to this 7, and you have 3, 4 with you. You know, this is how I'll keep going down. Now again, when I am at 5, I'll push this 5 inside it. Okay. And after pushing 5 inside it, I'll make a call to the left and right. So I'll push this 5, I'll have 3, 4, 5 here. And the left child over here is null, where maybe I can terminate. So this is the idea that we'll be trying to use. We'll have a vector with us. In that vector, we will push the current node, and then we will pass that vector to the next recursive call, which is to the left subtree and also to the right subtree. This is what we'll keep doing. What is the basic idea of backtracking? The basic idea of backtracking is that if you are doing something, you also have to undo that thing. Okay. So it means, let's see, when you are at this node, you are pushing this node inside this list. When you have pushed this node inside this list, you make a call to left, you make a call to right. That's totally okay. Now you are at 4, you push this 4 inside this list. And then you make a call to left, you have 3, 4 at this 5, and you make a call to right, you have 3, 4 at this particular thing. Now, when this particular recursive call is over, should you not remove this 4 from the list? Because when this call is over, you will come back over here. And when you come back over here, you will start considering these paths that go in this direction. Now, the paths going in this direction will not have 4 in them. So it's your responsibility to remove 4. So whenever you are at a node, the first thing you do is you push that node. And after pushing that node, you visit the left subtree, you visit the right subtree. So far, everything is okay. But once you have visited all the paths that emanate from that node, now it's responsibility to pop that node, because if you do not pop that node, that will be reflected in the other paths as well. So this is exactly what backtracking is. You do something, so pushing is like doing something, and then you make your recursive calls, and then you undo that thing. Undoing means, in this instance, you just pop that particular node. As simple as that. So this is what we'll be doing. Now, if you take a look at the code, it goes something like this. So let's say I have got a method called as print paths. It is void because it does not return anything. It simply prints all the paths out there. Okay. So here you are passing the root of the tree and you are passing a vector. So let's call that vector as temp. Mind it, you are passing it by reference. Okay. because whatever change you have done to this vector, if you have pushed this 3, you want that push to be reflected here as well as there. That is the reason you can't pass it by value, you have to pass it by reference. Okay, so let's say I want to write this code. Let's first talk about this idea. This is what you do whenever you are at any particular node. So whenever I am at a particular node, the first thing that I do is I push that node in my vector root data. This is what you do. And after this, what is the next step? The next step is to make a recursive call in the left subtree. Making a recursive call in the left subtree means calling print paths for root left and passing your temporary vector. And then you will make a call to the right subtree also, which is rooted at root right, and you will pass your temporary vector. Do you see that I have pushed this thing and then I have made a call to my left and right? Why? Because I know for sure that all the paths in my left subtree and in the right subtree will contain this node. That is the reason after pushing it, I have made those 2 calls. But when these 2 calls are over, that means I have visited the left as well as right subtree emanating from this node. Now this node is no more useful for me because now in the other paths, this will not be reflected. So now it is my responsibility to do temp.popback. So this logic is your backtracking logic. This is what I had written over here. In this code, there is something which is missing. And what is that? Termination condition. So what will be my termination condition? Okay, how about having a termination like that? I can say, okay, like look at this scenario. 5 left means you reached null. Keep looking. You reached null. And by the time you reach null, you have the data of this path in your vector. So you can maybe print it. So I can say that, hey, if my root is null, then I'll have a logic over here which will print the contents of this temp. And after that, we will return, we will exit. So can I have this simple termination condition with me? Yes or no? So this is quite interesting. A lot of people who even I have interviewed, I have seen they write such kind of code, and this code has a major flaw. You know what will this code print? So for that, you can just focus your attention over here. See, this is already the recursion tree diagram of this code already. So you were at this node, you pushed this 3, and you made a call to the left child, and then you made a call to the right child. Now again over here, you pushed this 4, and that way you made a call to the left child and then the right child, 5 and 7. Now again at this 5, you will push this 5 inside it, and you will make a call to the left child and also to the right child. Okay, also to the right child, 3, 4, 5. Now what will happen here is, this is the case where the passed node is null. So you will print 3, 4, 5. And this is also the case where passed node is null. So again, you will print 3, 4, 5. So what has happened is you have printed this path 3, 4, 5, not just one time, you have printed it 2 times. So that's a big problem over here. And you know, this problem will only amplify. Think of it. By the time you are here at this node, when you are at this node, what will you do? You will push this 2 inside this vector, and you will have 3, 2, and you will make a call to the left child of 2. The left child of 2 is null, right? Now again here, because this is null, you will print 3, 2. Now tell me one thing, do you want to print 3, 2? Do you want to say that 3, 2 is a root to leaf path? The answer is no. Why is the problem happening? Because the way your code is written, the way your termination condition is written, you are trying to print root to null paths. You are not printing root to leaf paths, you are printing root to null paths. So if I attach the null, this is one null, this is another null, this is one null, this is another null, this is one null. So in reality, this code will print 3, 4, 5 at this null, 3, 4, 5 at this null, 3, 4, 7 at this null, 3, 4, 7 at this null, 3, 2 at this null, 3, 2, 9 at this null, 3, 2, 9 at that null. So in questions like these, whenever you see that you have been asked to print all the root to leaf paths, or you have to do something at leaf. If the question is a function of leaf, then instead of terminating at this particular thing, it's better to terminate at leaf. So this is a really, really important point to understand. So how do I fix this code? So what I'll do is I'll just make a few changes over here. So let us erase it for now. Okay. So what I'll do is, let's say I was at 5. At this 5, I pushed this 5 inside it. When I pushed 5 inside it, I got 3, 4, 5. But once I got 3, 4, 5, then I do not need to make further calls. Why? Because this 5 is a leaf. So over here, I'll have some condition. Okay, just look at that. So I'm going to write something in this part. I don't have space, so I'm writing it here. So I would say if root left is null and root right is also null. If that is the case, that means the current node is a leaf. And if the current node is leaf, then I'll print the contents of my temp and then I'll return. That's it. And if that is not the case, then only I'll make a call to the left, I'll make a call to the right, and then I'll do a temp dot pop back. This is how it will happen. Okay, so you can put this thing in an else condition from here to here. So this thing will make sure that when you are there at a leaf node, when you are there at the leaf node, you are pushing that leaf node, but after making that push, you are checking whether your R is leaf or not. If your R is leaf, then you are printing the contents of your temp, and then you are just returning. Okay. In fact, this return would not be needed over here because you eventually have to pop back as well. You just print the contents of your temp. Otherwise, you are doing these two things. So if you are at a normal node, you push it and then you make a call to left and right. That is what you are doing over here. And then you are popping back. Okay, now some of you have a very good question that, hey, in that case, what to do if certain times the root is null? And that can very well happen. See, if you are at this node, you might make a call. In fact, you will make a call to your left as well as right, correct? Now, when you make a call to your left, if that is null, then because of this check, you will get null pointer exception. So what to do? You will add one more check over here. If the root is null, just return. Don't do anything. So it means that if you have ever reached at null, at that point, you will have 3, 2 in your array. So at that stage, you don't have to do anything. You simply return. Correct? You know, similar sort of thing we had done yesterday also when we had written a program to calculate number of leaves. Do you remember that? We wrote a program to calculate number of leaves, and there as well we had two termination conditions. First termination condition was at the leaf itself, and the second termination condition was whenever our root got null. So we are doing exactly that over here. If we touch a path, if we ever stumble upon a null, we are not going to do anything. Otherwise, the first thing that we are going to do is we are going to push the node. Now, if the node is a leaf, we are going to print the contents of array. Otherwise, we are going to make a call to the left and right. And finally, we are going to pop whatsoever we had pushed in the array. Any thoughts about the time complexity of this program? It's an interesting question. Lot of people, even good programmers, make this mistake. When I ask this question that what is the complexity of this program? So if you're making this mistake, no worries. Let's learn through it. Let's say you have a tree which looks like that. Okay, how many root to leaf paths will be printed for this tree? Only one. And what is that path? That path is 1, 2, 3, 4, 5. Let me write it. 1, 2, 3, 4, 5. Okay. Do you understand it here that each integer is printed only once? 1 is printed once, 2 is printed once, 3 is printed once, 4 is printed once, 5 is printed once. Okay. Let's take some other example. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. How many root to leaf paths will be printed here? 8. Okay. And what is the first path going to be? 1, 2, 4, 8. Second path will be 1, 2, 4, 9. 1, 2, 5, 10. 1, 2, 5, 11. And then you have 1, 3, 6, 12. 1, 3, 6, 13. I hope I have not missed something. 1, 3, 7, 14. You can check that. 1, 3, 7, 15. Okay, here also can I say that each integer is printed only once? The answer is no. How many times this 1 got printed? 8 times. 1, 2, 3, 4, 5, 6, 7, 8. 2 got printed for 4 times. 3 also got printed for 4 times. You know, there is a very strong reason why. Because how many paths cross this 2? 1, 2, 3, and 4. Similarly, there are 4 paths that cross this 3. So you can see that 2 has got printed 4 times, 3 has got printed 4 times. Now, how many times this 4 has got printed? 2 times, because there are 2 paths that cross this 4. So 2 times this 4, and this 5 also has got printed 2 times, because the first path is this, second path is that. Similarly, this 6 also 2 times, and this 7 also 2 times. Okay, how many times each of these leaves have got printed? Each of these leaves have got printed only one time each. So 1 time this, 1, 1, 1, 1. Okay, now let's be realistic. What is the total number of prints at first level? Total number of prints at first level, 8, correct? What is the total number of prints at second level? 4 plus 4, again 8. 4 times this, 4 times that. Total number of prints at this level, 2 plus 2 plus 2 plus 2, again 8. And total number of prints at this level, 1 plus 1 plus 1 plus 1, again 8. So I can say that at each level, the number of prints which is happening is 8 only. This is a point which is worth noting. Now what I can say is that if the tree is perfectly balanced and there are n nodes, then how many levels will be there? Or what will be the height? It will be log of n base 2. Okay. It will be log of n base 2. And now think and say, if there are n nodes, then roughly how many nodes will be there at the last level? Roughly n nodes will be there at the last level. And you know, it is something which is very, very easy to understand. You know, last level has maximum number of nodes in case of a perfect tree like that, because you can see here the total number of nodes are roughly 15 nodes, and out of 15, 8 nodes are there at the last level. Okay, you can cross check that. It can be mathematically proven as well. So I can say roughly n by 2 nodes, which is half of the nodes will be there at the last level only. Okay, half of the nodes will be there at last level. So I can say that each of these nodes will get printed 1, 1, 1 time. Okay. Now each of these nodes will get printed 1, 1, 1 time. 2, 2 times. Each of these nodes will get printed 4, 4 times. Each of these nodes will get printed 8, 8 times. So I can say that if there are log n levels, right? And if there are n by 2 root to leaf paths, because there are those many leaves only, then total complexity will be n by 2 into log n. This 2 can be ignored, so it will roughly be n log n. Now, what is this n by 2? This n by 2 is simply equal to number of leaves. Number of leaves, which also symbolizes number of root to leaf paths. So it means that there will be n by 2 paths which will contain 1 in it. Similarly, there will be n by 4 paths which will contain this, and n by 4 paths which will contain this. N by 4 plus n by 4, again n by 2. N by 8 paths which will contain this, n by 8 paths which will contain this, n by 8 paths which will contain this, n by 8 paths which will contain this. Again, n by 8 plus n by 8 plus n by 8 plus n by 8 will be n by 2. So I can say that there are almost log n levels, and at each level, the number of prints that is happening, that is almost n by 2, which is n. So total data which will be printed will be almost n log n, where n is the number of nodes. So a lot of people who say that the time complexity is going to be order n, that is not right, because when the tree is balanced like that, then a particular node will be printed again and again. Okay. And this is quite contrary to the case of a skewed tree. In case of skewed tree, only a node will be printed only once.